this Spanish saying, es de bien nacido ser agradecido. On behalf of the organizers, Javier, Eduardo, Rodrigo, and myself, I would like to thank, okay, I wrote, I don't want to miss nobody. So first, lecturers and speakers for their wonderful talks, really, we enjoyed a lot. Also, Nathan Berkowitz, the director of the ICTP here in Sao Paulo, Larissa Takeda, Humberto Neto, Eduardo Sato, and all the people from the Principia Institute for their support, okay? And of course, we would like to thank all the participants who we hope enjoy the talks as much as we did. So, gracias to all of you. Thank you very much. So now, Caio, please. Caio is going to talk about beyond translation symmetry, strongly disordered and amorphous topological insulators. Okay, please.
So thank you very much for the invitation. It's has been a wonderful week and I learned a lot. So today I'm going to talk about strongly disordered topological insulators, and I fit in here topology and condensed matter. So the other subjects I know very little. So I hope I'll start with some physical motivation. And so the background of whatever I'm talking about today is the quantum Hall effect. This is standard condensed matter physics course. And basically the idea is that if you have a two-dimensional system, low dimensions, then in a large magnetic field, then whatever you would expect classically, like this dashed line, you see like the response gets for the transversal resistivity gets some plateaus and these peaks. And these plateaus have this incredible feature that they are precisely quantized. So doesn't matter what kind of system you have, doesn't matter as long as you have low temperatures and large fields, and the geometry and all of this is not there. It's just universal, and actually this is now a metrological way to define quantities that depend on charge and current. And the interpretation of that early on was in terms of Landau levels, and the fact that you have a constrained geometry, and eventually you have to contain your electrons, and actually you always keep channels open, and depending on the position of the Fermi energy, you have a quantized number of channels open, and the other feature is that the current is chiral, so in one edge flows in one direction, the other edge flows in the other. And so the first hero of today is David Fowles, who reportedly was very unhappy about this explanation, because the standard theory for transport at that time was Kubo and linear response, and you should actually not work a Mickey Mouse kind of model for every new feature you have to have a unified view. And so he said that this project, and eventually he wrote this very seminal paper where he made some calculations and predicted actually that the conductance, the transversal conductance was quantized, and this is a very important paper in the field. And 2 years later, Barry wrote a paper on Barry curvature and Barry phase. And these two guys got together, and actually they understood they were talking about the same thing. So this is what José Hoyos will call the first fortunate event. So actually, Barry was thinking about, having a a system which is or something that is adiabatically changes adiabatically and encloses a circuit. So this parameter psi for Barry was a very abstract one, and for David Fowler's this was just the Brillouin zone, if you want. So the Perry curvature comes in. And later on, people explored on that and understood this is a long thing to understand and discussed in the mathematical literature, and this was associated with the Chern number. So the second hero of the talk is Doug Haldane, and basically he asked himself, well, what about, is it possible that I have this quantum Hall effect without a magnetic field? So, and then he set up this model here, which now is the H0 is what we call the graphene type binding model. At that time, there was no graphene. So there was, you know, like electrons jumping in a lattice, a honeycomb lattice. He introduced the mass term, and he introduced some magic, which would introduce chirality. So electrons flowing one direction, they pick a phase. The electrons flowing the other direction, they pick another phase. And he studied that model. And he figured out that he could write Chern number for that. So he understood that this system had topological properties. And he wrote the phase diagram for that. So in terms of the parameters of the model, the angle phi, the electron will pick every time he will go around, and the mass with respect to the term that is associated to chirality. And the phase diagram looks like that. And C1 is a trivial phase. These are topological phases. He understood also some aspects of how the electrons will circulate in the system. And he actually had the first discussion how this phase transition will go. So in order to go from non-trivial phase to trivial phase, you have to close the gap. So this is a region where actually there is no gap. Here there is a gap, there is a gap, and here you close the gap and then you cross. And so there is a whole discussion on that in his original seminal paper. Okay, so that's a very important paper in the field, and I couldn't resist. So it has one wrong prediction and a very good prediction. He says, this particular model present here is unlikely to be directly physically realizable, and you know, blah, blah, blah. This is, we'll see that this is very wrong. And the quantum Hall effect can be placed in a wider context of phenomena associated with broken time reversal, symmetry, invariance, and topology. And he couldn't be more right with that. And actually, the generalization came a few years later, actually almost 20 years later, when Ken and Malley actually, they made two copies of the Haldane Hamiltonian. And instead of having just a chiral movement here, they'll have helical states. So they consider two spins. Haldane considered spinless electrons. And then they came up with this idea of a topological insulator. And in real materials, this magic term introduced by Haldane is the spin-orbit interaction. Okay, so this is the background. So for the ones that are not really familiar with that, suppose that you have a gap here. You have your valence band, conductance band, and you have some external parameter that you can control the Hamiltonian. You change the gap. You are still a normal insulator, and then eventually close the gap. And if some conditions are met, eventually you become a topological insulator. And you know, you might cross again or not, but this is the way things go in general. So the idea is that here you have a topological transition. This situation here is associated with a topological invariant. Here I put C in because I don't have any other one to discuss so far. And there are some properties of the Brillouin zone of the states, of the occupied states. They can think about the fiber and K space, and they have some particular topology. And basically here you change the Chern number in this transition, and the magic is always for us spin orbit. So this is the background. Good. So now I'm talking about band topology. We had some attempts here, or some talks. We're discussing topological states in strongly correlated systems. This is a very open question. Here's things are pretty much well defined. So what you expect is that if you have a two-dimensional system, oops, yeah, well, I think it's gone. So I'll point. I'm very tall, but this is beyond my capability, you know. Sorry? Yeah, it's working, but it doesn't hit. Okay, it's very weak. Okay, so if you have a two-dimensional system, basically the idea is that you have these edge states, and they have this helical structure. And there is this bulk-edge duality, because in the bulk they are insulator, and they have these edge states here that cover, you know, like the gap. Typically you have a Dirac cone. And what is very important for us in condensed matter is that these states are topologically protected. So whoever works in condensed matter, very often you have edge states or surface states, but once you have a dirty system, they go away. And here the prediction is that this is very robust as long as you keep time reversal symmetry. In 3D is a little bit more complicated, and I have stolen this, oops. This is recorded. So I have picked this from the internet. This is a bad drawing, because the surface states here, they are not, by no means, unless you are ballistic, they don't have lines like that. They do some funny thing, but it's a surface states and not the edge state. And again, there is this bulk surface duality, there is a spin texture, and this has been measured, and there is topological protection. Good. So the first, I'll stick to 2D for a while, and in this talk actually, only at the end. So the first very important, or the experiment that actually is the most quoted thing here is a realization of a topological insulator based on quantum wells. And of a particular material that has a very large spin orbit. And this is by this group of Lewenkopt, and this was the theorist, very bright guy, that was involved. And so this is the, you know, theoretical view of things. So you have beautiful edge states with helicity and a confined geometry, and this is reality. So if you have a short wire, then you see this plateau as predicted, quantized states. And here's a blow up in that, and it's a lot of noise. This is by no means the precision required by quantum Halls, so this is very puzzling, or was very puzzling. And if you have larger or longer wires, then they behave like you know, regular wires, and no quantization. So there is a long discussion here, including some guy that has worked very nice papers here in São Paulo, experimentalist. And so the puzzle is, if you have a longer wire, then why should everything go away? Because if you are protected against disorder, you should observe the same in a short wire or in a longer one. And then there are very few realizations. One that I want to flash is a very different material platform. This is a TMD, it's a 2D crystal. Again, you have a very strong spin orbit, and this has been published 6 years ago, 7, and by Pablo Hariri, who always produces nice thing. But the same thing, you know, you have this noisy thing, no quantum Hall standard, integer quantum Hall standard. If you have a large device, then it tends to destroy this integrability, or this quantization, shorter device behave nicely. So this is the puzzle. So hundreds of theoretical papers try to explain that. And so some people are fans of inter-edge backscattering. So you have your electron flowing, for instance, here, you two-edge status, and then there is some disorder that connects, both edges. So the theory is actually for a very large system where this is not possible. And then, well, okay, so if the experiment enables this channel, then eventually you spoil the whole thing. So this is not a very, people that went to this path didn't got very far. And the intra-edge is more like the standard. So you have a spin up or a spin down flowing here, then it hits some mechanism that has some spin flip, and then it scatters back. And this is actually, so the theory says that you don't have, that you need to have time reversal symmetry. And if this is a magnetic impurity, then your safe theory is fine, but the experiment won't see the nice features predicted by the theory. So people were saying, well, you have lots of magnetic impurities, so the experimentalists work hard for years to acquire 10 to the minus 7, 10 to the minus 8. So they say, no, this is not a mechanism. Then there are very convoluted mechanisms that theorists have proposed. And so I'm more or less a big fan of that. And for the one that is with the TMDs, we have a paper where we have non-magnetic disorder that induces this backscattering. And the idea is very simple. You have, in these TMDs, you have lots of edge disorder. So the edges are very irregular. These edge disorders cause localization, for instance. And you have localized states there. And then if the system is, the electrons are interacting, you have a large density of states there. And then it's favorable for the electrons to actually polarize and get magnetic. So this is the Stoner instability. And we were able to explain the features of the experiment, of the TMD experiment based on that. So you have rough edges. You solve some self-consistent equation, mean field with Hubbard term or whatever. And then you see an onset of magnetization every time you have an edge which is, one of these dents which is relatively large. And then, the transmission is very fastly suppressed. So this is just an advertisement. So this is, now we are, after 20 minutes, we are now in business. And so topological insulators and strong disorder. Good. So this is the main thing. So what we saw so far is that disorder can, in many ways, be detrimental to observe this, let's say, the topological phases. But now I will take a different turn and think, well, the theory says you have a topological insulator or topological material, and if you put disorder, it's protected against disorder. So can I formulate a theory in terms of to understand what's going on? Because disorder actually breaks translation invariance, and so the whole formulation in terms of integrals over Brillouin zone, it's not it's not really applicable. So how robust is protection? So does it make sense to start with a theory that doesn't consider disorder at all, and then you have a topological thing? And the paper that really attracted my attention was this PRL, almost 10 years ago. And these guys, very bluntly, they put forward a model where you have a really random network of sites, and the electron is jumping around. And then locally, it looks pretty much like the Haldane model. right? But globally, you don't have anything like order. So that is very, I mean, I throw away everything, or any hope of formulating a simple theory in terms of Chern numbers, etc. And these guys actually observe this quantized conductance, edge states, etc. And it's a very nice paper. So, and that was the setting. So, okay. And then they call it, oh, sorry. Yeah, it's a little bit misfortune that they call it amorphous. This is a random system. It's like a Boltzmann gas. It's not amorphous. And so it has very little to do with actual materials. Because an amorphous system, as we know, is something that has short-range order and loses long-range order. So, I mean, this 100 years of knowledge on that, there was a boom with, you know, solar cells in the 70s, 80s, with germanium, silicium, amorphous to understand, to do things. And people put up some models for that. They have simulations. And back then, they would do simulations with 1,000 atoms. So there's some people here laughing because this is zero, it's very small. And they developed some criteria to classify this amorphous system. And one of these things is this radial distribution function, and basically tells you where is your neighbor, where are your neighbors when you're sitting here. So you see that you are able to say, oh, my nearest neighbors is at some fixed distance. Then I have some information about the second, the third, and then poof, then I lose information. So this is a real amorphous system. And so more books. So how does it look in 3D? So this is a gas, which was done by the PRL. But if you have a 2D system, this is the way. So we didn't have a good answer to classify or good understanding of this whole behavior in terms of some invariance. But we had the idea, okay, so can we propose to the experimentalists something that would be a topological insulator in an amorphous phase based on bulk edge duality and things that we can compute. And that was our first project on that. And it was inspired by some experiments that people had in bismuthine being a topological insulator as a 2D material. This is a science almost 10 years ago again. And that experiment has the beauty that if you read it carefully, you see that sample preparation, the guys spend weeks annealing this thing to get it really nice. And so our idea was very simple. Okay, just go to them and ask them to do a lousy job. Don't anneal for weeks. Anneal for just a few days, and then you have an amorphous system. And you save your time, and you can produce new interesting physics. And so these are these two papers. And basically, we developed some way of simulating some let's say, amorphous system. And this is not my field, but this is hard work by people that do ab initio calculations, density functional theory. So it's a code that people put the forces of the atoms, compute them quantum mechanic, let them relax, and so this is state of the art, the best you can do for a cell, which is again 1,000 atoms or 2,000 atoms. And we see what is expected from the from the structure function and radio distribution function. Sorry, you have this peak and then it loses. And then concerning bulk edge duality, as you start making your system amorphous, then eventually the plateau survives. It's eaten at the side. These are localized states that degrade the plateau, and I won't have time to discuss that, but so that's the thing. So, sorry? No, this is just one. And the thing is that it's a little bit boring because if you average one, it gets one. So you have a quantized state here. So it's we have several different realizations. So sorry, just a joke. We have several different realizations. This is always preserved. So this is the So the idea is that we expect the experimentalists to have a region where it's quantized, and that's or at least they can do other things like measure edge states, etc. So, no. Yeah, if you do that, if you ask that through experimentalists, you basically will like to kill you because it's a lot of work. So. This paper actually got a lot of attention, but unfortunately only from theorists. Not well. It's well cited. Experimentalists don't like that. Yeah. So if we have small ones, then you don't degrade here. If you have very large systems, and these are relatively large systems, you see that if you compare the short one with a large system, then the large one eventually get a little bit more degraded. And we have a theory for that, but I don't want to, I mean, we understand that in terms of localization, and this is not the main thing here. I don't want to dwell in too much on that. That's part of the story. So here is my story. So if you look at the band gap, as you amorphousize the system, it stays always open. So it's incredibly robust. And then I asked these guys to do something they don't like, so to play with the spin-orbit coupling. They say spin-orbit coupling is ab initio, so it's given, I don't know, by God, so you don't have to play with it. But I wanted to see how it works. And then if you make the spin-orbit coupling weaker, eventually you get situations where the gap closes and the system makes a topological phase transition. And so there is something to be understood in terms of you know, like deeper. So why the system is always robust or not robust? Can we understand this behavior in order to give the experimentalists further motivation to invest in this thing? And okay, so and then these are the goals. Can one understand when the topological phase survive or not? What is the order parameter of a topological phase transition driven by disorder? What are the scaling? Is there critical exponents? In the absence of translational invariance, can one characterize the topological phases by a mathematical rigorous topological invariance? And this is what I'm going to talk in my, I have 25 minutes, that's good. So, in order to begin, what is the common knowledge about topological phase transitions in this kind of materials, or in general, so band topology. So suppose you have a Hamiltonian which depends on some parameter, h lambda 1. If you change this parameter and you go from here to here and you always keep the gap open, right? So no matter what you do, you are topological. So gap open, this is topological. You go from here to here. You can put a lot of disorder and you're still topological. That's the prediction. So if your parameter lambda gives you this trajectory, then eventually you go to a trivial state, and then eventually you end up with a lambda 1 and another gapped Hamiltonian, which is topological. And okay, so then you go here through two phase transitions, and you are still here. So this is nice, but doesn't tell you, you know, what happens in a real system. So you might have very odd trajectories here, and this is what you want to understand. And so the first one is the first paper we try to understand that is to understand better the phase transition. And this was a collaboration with Gerson Ferreira from Uberlândia and his student Brian. And actually it's inspired by people that were looking at topological Anderson insulators. This is a very old work. And what people realize is that disorder can drive your system from normal to topological. Very strange thing. So how can we understand that, right? So the idea is that, oh, this is bad. So the idea is that this is a drawing of the disorder potential, the strength of the disorder in an Anderson model, and this is the Fermi energy. And you can sit here where you are, where you have almost zero or some kind of conductance which is different, and then by cranking up the disorder, eventually you might end up in a situation where the conductance is 1 and you are topological. So and this is what we wanted to understand better. So in the model we choose to work with is the BHZ model, which is the model that describes this mercury telluride topological insulator. And we put Anderson disorder. Anderson disorder is like you put a lot of uncorrelated disorder. And so when you put a strong disorder, and we had a more, we choose some parameters where you are more symmetric, you have particle hole symmetry, we explore this direction here. We stay at Fermi energy here and crank up the disorder. So for some disorder which is not all that strong, you have this kind of flows. And then for a disorder which is around here, then you see that the electrons, they organize and basically they like to develop edge states. And you have a very large disorder, the system localizes, and you have a second phase transition. Yeah, sure. Yeah. Yeah, I'll go to that. Here, actually. so I inverted things. Oh, sorry. I pressed the wrong button. Sorry. I want to go back. Okay. Yeah, is that? Did I jump something? Yeah. So how do I characterize? Okay, so you are fast. So the Chen number, for instance, is defined in this way. And then many years ago, people introduced a way to characterize, to introduce a local marker, which is basically, it's more than that, but in a pictorial way, you can think, well, here I have an integral over K space, and I might think about doing something like, a Fourier transform and work with an integrand, which is a coordinate space like. And they invented a good way to do that, and by introducing some suitable projectors, you have this local marker, which is proposed by Bianco and Resta, and so there are sophistications due to different authors. This has some properties which are not so desirable, and there are lots of more recent improvements here when you have a spin-orbit interaction, etc. Wei Sheng worked on that also. He has a number of papers. And so when you compute that, you have a local marker, which in principle should work. It gives you, if you look here at this graph, it gives you something like, in the clean system, something like a nice Chern number of 1, local. And the bad feature of this particular implementation by Bianco and Resta is that if you integrate over the whole space, it has to be 0. So it has to be, whatever it's topological here has to be compensated as the edges, and it's not easy to interpret that. Once you put disorder, you see that the local marker goes up more than 1. and there are these things at the edges. So you see it's not 0, so there is something topological there, but it's a funny thing. And if you go to very, very large disorder, then the system is localized, and there are some islands where there are fluctuations. And basically, clean system, you have this nice density of states. Here you almost seem to close the gap, but there's a finite size effect. And here you have lots of localized states that spoil all the fun. So, huh? No, there is no band structure. Yeah. No, I mentioned brilliant zone. I'm sorry. So if I did, no. This is a real space. I compute. This is not a brilliant zone. I compute the local marker across the whole sample, right? So this is the okay. So you mentioned if this was not clear, I'm terribly sorry. So the idea is that here you have a brilliant zone. Okay, so, but then by playing this kind of trick, okay, so if you go to a different representation, you end up with a local marker which acts, that you can evaluate at each point of your system. What would be ideal is that you integrate the local marker in the whole system, you get recover the Chern number, but it doesn't work that way. There are some ways to fix that. I mean, there are lots of former students of Resta that are working on that, but it's like a construct, you know, like here you have a real rigorous theory to justify that. And here you have a sort of a beautiful thing that you derive from here, but here you always assume that you have a brilliant zone. And so if you go from here to anything else, the underlying hypothesis is you start with a thing that has a brilliant zone, and at the end you have an expression that you don't need to invoke the brilliant zone, but you shouldn't forget where you are coming from, right? So that's the bad thing. Yeah. Yeah, you can, and yeah, you can do that. But at the end, I'll flash some other thing, which I think is better. So among different possibilities. So, and then we studied the phase transition. And what we understood is that actually all this nice, oh, sorry, I'm pressing wrong here, the wrong button. So if I go from here to here by increasing the disorder, actually, by doing some self-consistent Born or some diagrammatics, the other way to cast that is that the self-energy gives a correction to the mass term. And so instead of changing the mass term in a clean system, I change the disorder and thus the mass term. And this is the guy that drives the phase transition or the system to topological. And then we studied, you know, different ways, the scaling of how do you go from this phase. We compute this C0, which is the local Chern number, local Chern marker at the center of the system, and we find some nice scaling, and we found some critical exponent, whatever that means. But well, it's not Landau kind of theory. But actually, what we understood is that this kind of analysis is very useful, but has limitations. But in any case, what was surprising is that we got this critical exponent for this disorder-driven phase transition, and for the BHD, Haldane model, Kane-Melley, all the 2D models, it's always 2. So somebody wants to understand if this is really universal, be my guest. So that was the result. But then the bad thing in this model is that you have a lot of, you put a lot of disorder, so we want to understand something which is more like related to experiments, a structural-driven transition. And then I teamed up with Marcelo, who is my colleague, and 2 students who left, unfortunately. And we actually made this progress on having a model that you can start with a real crystalline system, go to some intermediate phase, and eventually get to something which is amorphous. So this is a typical, like diffractogram. Here everything is blurred, but you still have something intermediate. And this is a typical thing of an amorphous system. You have the center, you have the first neighbor, the second neighbor, and then you lose information. This intermediate thing, Marcelo teach me, this is called Hosemann paracrystals, entirely new thing to me. And but the thing is, it's very difficult to make this bridge and to make the simulation. So before we do that, so this is what people call type 2. I mean, Anderson called it type 2 kind of defects, in distinction to type 1 that I discussed before, point defects or vacancies. Here is just like you have a lattice distortion, so that the Bragg peaks are no longer delta functions. Here they are still delta functions, but you lose them eventually. Let's see. And so there are many ways to generate them. Irradiation, codeposition, quenching, doping, etc. People working in this kind of field know very much about how to generate this amorphous systems. But to model them is hard to make this transition here. And we went to several different ways on the literature that people would do, and Voronoi, Gaussian method. So this is always for real amorphous systems, and he wanted to have this crossover. And then my student actually, who is crazy about programming, he found a way, a kind of a noise, a method to make things smooth, called Perling noise. And this guy even won a prize for that. Actually an Oscar. It's not related to physics. But it's a very sophisticated way in computer graphics to generate smooth kind of patterns. And so, Victor was, I don't know how he got to that, but the thing is that he implemented that to generate these intermediate structures. And actually, the paper is more known for that than for the physics, but whatever. So, and then to get you some insight on that is let's stick to a model, this half PhD model. So I take one edge only, and we make a case study, the crystalline system, and we vary one parameter here. And then actually what you see is that the points of crossing when you go through a phase transition of touching in the brilliant zone, they are different. And you can see it better in this target space when it crosses the origin. And the topological transitions are just the points when the target space crosses the origin here. And then you can understand negative to positive Berry curvature. And this is crystalline, so I can work with the standard things. And this is the kind of transition I was looking for using just churn. And this is a well-known thing. So there is a competitor to churn, which is also a local measure, which is the bot index. And then you can vary M. And I could do churn again, but I wanted to show that bot and churn are the same. And so it works perfectly fine for this model. And so we have a global thing, which is good, which is local. This is not a construct. This is more like more fundamentally done. And so we can try to understand how robust are the topological phases when you put this order using not a local marker, but a global marker, which is, bona fide. It's mathematically rigorous. And then, so that's the idea. So we try to understand is this churn or bot? This is bot. So for the clean system, we vary the two parameters, the mass and the lambda, and this is the phase diagram. And then we selected 2 points here to see how they behave as you increase the disorder and you amorphisize the system. So the idea that you have the blue guy if you are in this blue guy, your arrow is in the blue guy. So this is very robust. We wanted to understand if you are outside or in the margin of the blue, if you still survive the process of amortization. Then we get some insight on what are the requirements to be robust. And so, oh, I'm bad. And so the first one is like we selected this blue point, which starts at the red region. And if you amorphize it, it's gone, the red region. And the bot index goes from 1 to 0. So it stays outside the blue. So you go from a topological to a trivial. How do we understand that? And in distinction, if you are in this blue point, then life is more interesting. You start topological, then the red region disappears, but the blue for this particular position expands, and then you end up with -1. So you go from topological, trivial, topological. So you make a transition. So how do you understand that? And for that, we go back to the clean system and study how the band structure changes as a function of the mass parameter. And then what you see is that you have a tilt and of these graphs. And I mean, here you have the bands, they touch at the edges. Here they touch at the corners, at the edges, and here they stay at the center. So the robustness of a system depends on where these guys start touching for the clean system. This is what we understood. And here we play the game, the things that we learned from the other study. So how do you change the mass term realistically? So if you introduce the structural disorder, you actually address your mass, and the real part of the self-energy changes this, and so this is the way you actually go from one to the other. This will be the pristine, and here you go, this is the result of the simulation. And we have a theory for based on Hosemann paracrystal theory for the correction in the mass. It has to do with the structure function, how it relaxes, and et cetera, et cetera. And so this is the doom of the whole thing. So you start topological, eventually, this is the blue guy. You know? So you start topological, you actually become normal. So this is a finite size effect, should close the gap, and then you stay amorphous all the way. So the idea is that if you're close, if your band touching is at a gamma point, basically this is it. The conclusion is that you are always topological. If you are at the corners, then they are easier to destruct. And if you are at the edges, the same. And this we learn in condensed matter. So all the gap openings in the metal, it's just like things that happen at the edges of the Brillouin zone. So this is how you generate, with a small amount of impurities, a gap. So it has some resemblance to that. So, and this, I don't have much time, I will flash to that. And so the last thing I wanted to make in my list was, so can we actually have a topological invariant in real space? And the motivation of this work is that, well, as you asked and we discussed, there are many topological formulations in reciprocal space. This is very solid. And in real space, there is this bot index, but it doesn't work for 3D systems. It only works for 2. So we had extended to 3 very bluntly, and well, we were bashed for that. There are local markers which have some problems. There is no unified formulation. It's a construct. Then there is the usual cheating, the supercell method. So you just make it bigger and bigger, and you say, well, eventually you do. But this is really cheating. And so this is what we started. And then I teamed up with a guy who is a brilliant PhD student. He's an experimentalist, but he's working with topological insulators, and he was very disturbed by the fact that he's working with 3D systems and there was no good theory for that. And this is the mathematician that came up. And so the wish list is that you want to have a rigorous real space approach to construct topological markers or topological it has to be computationally fast and reproduce the literature results for 2D, which is solid. And eventually want to work over the whole periodic table of topological insulators. So just to remind you, well, several years ago, people had made a periodic table of topological invariants and classified all kinds of systems based on the Outland-Zirnbauer tenfold way. And here is what you can do. Z2 works fine for the kind of systems we are looking at, but this is reciprocal space, right? So and then Kitaev, always Kitaev, he was the first guy to notice that based not the same language as Outland and Zirnbauer, but he was thinking about K-theory that some superstring people here use in a different context, I guess. And he got more or less the same result. Well, the same result, but he didn't make such a nice chart, exhaustive chart. So the idea here is that we want to do something in real space, right? And then my mathematician colleague, he said, well, I mean, okay, so this is probably good. So what we standardly do is, for bot index, etc., is that you have something formulated in K-space, and you do something like a Fourier transform, because whatever is in the torus you can map in real space, and a Hamiltonian which has good K numbers, you map into that. And eventually the spectrum here, which is, like age as a function of K, you have a different spectrum here which doesn't depend on K. And there are ways to map one into the other based on like C algebras, which is a way to construct the algebras of these operators and the K theory. Now, the thing is, can we do that for a disordered system? And the answer is yes, for what people call in mathematics a coarse geometry. So you need to have your Hamiltonian formulated in terms of sites of a type binding model, if you wish, of Wannier states. If you start with that, then you can do the same tricks like here, construct an algebra for this coarse-grained geometry and apply everything you know from the K theory, and eventually end up constructing a topological invariant in real space, global one. And my colleagues decided this would be the nice way to represent. It's horrible. So it's like Z2 is also horrible to write. But, well, okay, so this is, they call it int2 whatever. So I wanted to give a different name, but involves a projector into a target space. You have to have a sufficiently large, you have to test convergence, but you have to have a sufficiently large amount of sites in yours. So you have to do some convergence, but convergence to 1 is nice, or -1. You construct the spectrum localizer in this region, and then you do whatever you do for Z2, the computation of Pfaffians. So we tested for the K-Melee model, so this is part of the story. And for the K-Melee model is a 2D thing, so people know other ways to do the calculations, even with disorder. And our topological marker is this int2, which is either -1 or 1. I insisted 0 and 1 is better, but no way. So -1 is topological, 1 is trivial. And what happens is that the spectral gap closes when you do this phase transition. And this reproduces extensive simulations by some previous guys that study exactly the system. Now, what is interesting is if you look at 3D systems where there is nothing there. And so we started with a clean one to see if it works for the clean one. And actually then for the clean one, we reproduce whatever is known. And for instance, you have a tight binding model for bismuth telluride. And you play with this parameter T, which is, you shouldn't do that, but because in reality, the parameter T is around here, but you can play to simulate a phase transition. People have done that before. And actually using our framework, we reproduce for the pristine thing whatever is expected for a phase transition, topological phase transition in a clean system. So this gave us confidence that we are doing well. And then we had this, put some Anderson disorder and studied how things work here. And we compared with the supercell method and things like that, which are not at the same status, but they also coincide. So we have a tool. So the thing is that we have a tool that we believe it could be used and incorporated even for people that do DFT calculations. In like, I think siesta is in real space. Yeah, siesta. Okay, so it could be incorporated in this. Good. So this is this paper. So we had done 3 things, right? So topological phases survive a strong disorder, but not always. And we have put forward a strategy to predict when they do and when they do not. This is paper with Marcelo. We studied some phase transition driven by disorder. Some people, Hui Sheng also did that for clean systems before, and other people. This is driven by disorder. And then we understood how the effect of this effective mass works, and we learned something from that. And then finally, very quickly, it deserves a real seminar. We propose a new real space topological index that is mathematically rigorous and applicable throughout the Kitaev periodic table of topological invariants, any dimension. And okay, so, and that's it. So this is the list of things I discussed. So this is previous work, and then inspired by that, we try to understand the nitty-gritty details, and this is the one that I discussed. So these are my collaborators. So there are some older people here. So and these are in green. They were students by the time they did the work. So yeah, well, I think with that this part of band topological insulators is in a good setting. I think we should actually approach interacting systems now. This is a real challenge. Okay, thank you very much.
I believe we have time for one question because we are a bit.
Oh, you mean with our theory? Yeah, it's in there. It's in there. It's so let's say this: given the system is a topological insulator in here in this region, one of the byproducts of our approach is that in real space you should observe as a projection into the system boundary and enhancement. This is what we can show. And this is what we actually observe in different settings. So if you have if you're in this topological region, then you see a surface here, which is, I mean, you have concentrated on a surface, and whereas if you are not, then you are just everywhere. So yeah, so this is one of the byproducts, yeah, of that approach. Okay.
Okay.
Good.
One more question.
Yeah.
Yes.
Interpolating between crystal and random things.
Ah.
But I guess the thing that you actually use from that is just the hopping
Yeah,
amplitudes?
yeah.
So couldn't you just vary the hopping amplitudes?
No, sorry. Not only the, I'm always pressing the wrong way, sorry. One way would be, yeah, you're right. One way would be to just change the hopping between these guys. The problem is that if, yeah, this is a technical problem. Once you want to implement this, the theory to estimate this self-energy, the effective mass, then I mean, we had to do we had to redo everything because it's hard to sell that just random hopping or some distribution of random hopping will give you a amorphous system, because then the sites don't do that. But for the electronic part, it will be fine. But then all the analytic thing that we inherit from Hosemann, we had to redo, because all this is based on the structure function and how you deform your lattice. And actually, I think the beauty of that is that you really deform your lattice, and you capture all the physics. You make a model which mimics all the physical aspect of this transition from crystal to amorphous.
The difference is that you also change the on-site energy in some way that's correlated. Okay.
Yeah, and the position and all that. But then you're right. I mean, if I only want the electronic properties, I don't need to do all that. But this is, I think, a nice model because it captures all the properties. Okay, good. Thank you.
Okay, we thank again Caio.
Okay, thank you very much.
Okay, next we have Hotat Lam, but let me see if he's already connected.
He's online.
Yeah.